So these NoSQL search roadshows, a lot of big names from NoSQL all throughout this year: Munich, Berlin, San Francisco, Copenhagen, Zurich, Amsterdam, London. My former boss, Danny Falco, real smart guy, Jim Weber from Neo4j, among other luminaries speaking, so I suggest you check that out. I'm Andy Gross. I'm Chief Architect at Basho Technologies. You can get a copy of these slides at that link down there, bit.ly/NoSQL Aarhus. It's actually hosted on Riak, so if you download those slides, you will be using Riak. My talk today is about the Dynamo paper and what's happened in the years since it was published. How many people are familiar with Amazon's Dynamo paper? All right. Well, no need, and this is actually an interesting point because every talk about Dynamo, or any complex system for that matter, I've spent the last 5 years giving talks about the database that my company produces, which is inspired by Amazon's Dynamo, and it's always the same review over and over again, and it's too information dense to really walk away with too much knowledge from it. So I'll give a brief overview and mainly talk about how Riak works, which is our clone of this system. But anyway, back to Dynamo. Dynamo was a paper published by Amazon in 2007, so it's a little over 5 years ago now. And it describes a collection of techniques, distributed systems techniques, that Amazon used to create a very high availability, low latency, key value storage system. So by key value, I mean basically the API is that of a hash table. You give it a key and you get an associated value back. Dynamo didn't necessarily really introduce any new concepts, but rather it took a bunch of techniques that had already been in the literature, that had already been used in different areas of computing, and combined them together for the first time. And if you haven't read the paper yet, it's one of the most accessible sort of computer science papers that I've read. It's really about how they built this system. It almost reads like an implementer's guide. But it's not bogged down with unnecessary theory. And I think that's why the paper was so influential, because not only is my company's database, Riak, inspired by Dynamo, but Apache Cassandra, Voldemort from LinkedIn, and several other lesser-known databases are inspired by this paper, along with a couple other papers that came out at roughly the same time. This is the mid-2000s. The Google Big Table paper and the Google File System paper are another two papers that sort of spawned this NoSQL movement, this sort of big collection, explosion of alternative databases that we've seen in the last 5 or 6 years. One interesting fact that I didn't know, and if you're a fan of reading these research papers, you'll notice Amazon doesn't publish a lot, that the authors nearly got fired for publishing this because it was giving away, in the opinion of their CEO, too much of their secret sauce. And I don't think they've published an interesting paper since. So how many have heard of Riak? All right, so a little more. That's cool, actually. Usually it's the other way around. More people have heard of Dynamo than Riak. So Riak is a Dynamo clone. There's this legend that I wrote it on the plane on the way to my job interview, which is only half true. I wrote something on the plane, and it didn't work at my interview, but I guess I got an A for effort because they hired me anyway. We call the code that I write at Basho technical debt. So I mostly talk nowadays. Mostly Erlang. Any Erlang fans in the house? That's fine. But it's mostly Erlang, and I'll get into some of the reasons why we chose Erlang to write the database. It's sort of an odd language choice. But with a little bit of C and C++ to interface with the very lowest levels, the stuff that touches the file system, like back-end database drivers. It's Apache 2 licensed. It's been around for a while. As I said, sort of first started on it in 2007, but we first released it in 2009, and we just released version 1.3 a few weeks ago. And nowadays it's had we have a commercial entity around it, and we have some pretty big customers. About 30% of the Fortune 50 companies use it. Chances are, if you're active on the web or on your smartphone, you're using it in some capacity without knowing. Just a little bit about my company. It was founded late 2007. The original people all worked at Akamai, the content delivery CDN company. And now we have about 120 employees with offices all over the world. We're the sponsors of the open source Apache 2 license project. And we also sell Riak Enterprise, which is Riak open source plus the ability to replicate among many data centers, not just two. We have customers that are replicating masterless rather, among 5-6 data centers. And we also sell a clone of Amazon S3. That's where the slides and that little bit.ly link are stored. But you can buy it as a product, run it behind your own firewalls for cases where Amazon is too expensive, or you have security needs or latency needs that Amazon can't satisfy. So the principles in the Dynamo paper were to have a store that is a data store that's always writable. And this is sort of a business need that didn't exist for a lot of companies until the mid-2000s. Before then, their needs were largely handled by relational databases. But leading up to Amazon publishing Dynamo or implementing Dynamo, there were a few very high-profile Amazon.com outages in the holiday season that were all traceable back to some failure of a relational database, Oracle or MySQL or whatever. And the example of what they were storing in Dynamo when they published the paper was Amazon's shopping cart. So when you think about it, for a shopping cart, it's much more important that the database accept a write than the database be consistent. In other words, if you have a clustered database and there's some sort of split brain syndrome going on and databases can't necessarily agree when you're putting something into the database about what the correct value should be, it makes sense for Amazon to accept that right and not drop whatever you were trying to put in the shopping cart on the floor, because that would be losing revenue for them, right? You always want to be able to write to this shopping cart, even if you can't get the exact consistent state of it all the time due to machines failing or network outages, whatever. So as long as the shopping cart can always accept writes, when you go to check out, then you use a more consistent mechanism where you make sure all the machines agree on what's in the shopping cart at the time of checkout. But while the user's shopping, you never want to say, no, I can't add this to your shopping cart because one of the database servers is down. That's a revenue loser for Amazon. And since then, Amazon's not the first to have that problem, but since then, a lot of business on the web is like this. If you're in the business of displaying ads, you don't want to display an empty advertisement because of some problem in some remote machine in your data center. You always want to display something. So being able to always write to this database, even if half the nodes are down, is one of the key sort of requirements from the beginning. Businesses on the web nowadays can get popular very quickly, virally, as they say. And you don't necessarily want to lay out a bunch of money for hardware ahead of time. You want to be able to incrementally scale as the growth of your website scales. So being able to add machines to the system one at a time, two at a time is very important. Just to re-emphasize, this is a fundamentally clustered database. We don't sell Riak, or people don't usually deploy Riak in node counts less than 5. So there's always 5 nodes here or more. Symmetrical, decentralized, heterogeneous. This means that all these sort of, at least symmetrical and decentralized, mean that each node has the same task. There's no master node, there's no slave node, there's no special configuration node. Every node is exactly the same. And if you've ever operated a business or a data center at scale, this becomes very valuable, because when you're got people messing around in a data center, the chances that they spill their coffee on some machine gets higher and higher over time. Or something bad happens to one machine. And if one of those, if they spill their coffee on the master, that's a big problem. So why not just have no master? Every machine in a cluster of Riak machines, or Dynamo machines, if we're talking about the paper, has the same exact role. So that means you don't have to monitor them in any sort of different way. You don't have to be more concerned if one goes down than the other. From a client view of the database, you can talk to any of them as if they were the same. It just makes things much simpler and cheaper to operate. Heterogeneous, meaning, you know, machines get more and more powerful every year. And if you start one year with, you know, a group of 5 machines, and then you buy 5 more machines the next year, the database should be able to recognize and take advantage of the fact that these new machines are more powerful and send more work to them, or recognize that they have more resources and treat them accordingly. And finally, these kind of data stores are typically the things that sit at the bottom of a large sort of service-oriented architecture stack. When you go to the front page of Amazon, that page, I think it's, last I read, 175 different internal services that get called to render the front page of Amazon.com, all of which have some persistent data store underneath them. So predictable latency is very important. If the latency of your database is all over the place, it's not a suitable foundation to build a very large service-oriented architecture. And this is accomplished with several of these techniques, all of which have appeared before in the literature. And to try to explain all of these in depth in the short amount of time I have would not work, so I'll cover them pretty briefly. Consistent hashing is one of them. That was a technique pioneered at Akamai, and that's how Akamai manages to get the right data cached in the right places so everybody has a nice, fast web experience without having to cache everything everywhere, or without having to move tons of data around when new servers are added to the network. Akamai used it for web caching. In Riak and in Dynamo, we use it for figuring out which machines a given object should live on. One thing I should state up front is that in Riak, in addition, you know, you're going to have at least 5 nodes. Every object is replicated 3 times by default. So it's a database for critical data that can't be lost. Vector clocks are a way to figure out how objects relate to each other. Since this database, as I said before, will accept a write even if the network is partitioned or there are machines down, means that it favors availability over consistency. Favoring consistency is something that traditional databases do. If you have a traditional clustered Oracle system or MySQL system and you want to write something to it, if the database in that case can't guarantee that every member of its cluster agrees on the same value, then it will refuse the write, because then it opens a chance that, you know, some node in that system that's partitioned off will serve old data, and traditional database systems value consistency over everything else. Vector clocks, since there can be divergent copies of data in Riak, are basically just a way to figure out how objects are related. If one is an ancestor of the other, or one is logically concurrent. I guess a good analogy here is if you use Git or Mercurial and you try to merge a branch into your code that you've already merged in, it knows that, and it's just a no-op. Or if you try to merge a branch in, sometimes it merges cleanly because the changes don't conflict. But sometimes 2 people have edited the same thing and you get a merge conflict and you have to go in and fix it. Vector clocks provide the same sort of infrastructure and the same properties for different copies of the same data in a distributed database like this. Read repair, anti-entropy, hinted handoff, gossip protocol. I have slides for, and I won't explain them here because I want to respect the time limits. So, hinted handoff. So we're dealing with a cluster database here. We're dealing with many nodes. This database is exposing a key value API. How do we decide where data lives in this database? It's a technique called consistent hashing, and what this ring represents here is, say, SHA-1 hash function. This is the hash function we use in Riak. The range of that function is from 0 to 2 to the 160th, which is a big, enormous integer. That's the range of numbers that that function can produce given whatever arbitrary input. The way we decide where data lives, let's scoot over here for a second to illustrate this, is if we envision that space, an integer range, 0 on this side, 2 to the 160th over here, as a circle. So 0 is at the top, as is 2 to the 160th. So this is 2 to the 160th over 4, 2 to the 160th over 2, etc. Right? So just basically take an integer range and wrap it around like a circle. Then, as you hash keys, so just keys in a hash table, they're going to end up somewhere between that range, because that's the range of the hash function. And then you visualize where that is on the circle. So hashing the key, go to, is some arbitrary large integer, and say it ends up here. These colored slices here represent different nodes in the system. So if it ends up here, you say, oh, pink's the primary node for it, and then we walk around clockwise, and we get green and orange. So that's why it's consistent. That's what I call it consistent, is because you can add nodes in here, and they just claim different little pieces of this, and that means that there's not going to be a complete rebalancing of data when you add nodes, but rather only little pieces where the new machines come in and claim space. It's a complicated concept, but that's roughly how it happens. So say a node fails. Say the green node blows up, right? And then you want to hash this key, blocks / this big UUID. Well, when you hash that, the value lands here. And again, we replicate 3 times, so we're going, the normal places this data would live would be on this one, and this one. But this one's down. Very simple, no problem. We just skip over it and pick the next one on the ring. Normally the data wouldn't live here, but any of these nodes can take requests for any of the other ones. So they sort of compensate for each other when things go down. And then if you were going to read that data again, the read request would see that this guy's down, and it would read it from here instead. This all works out to, sort of very nicely in failure scenarios. Nodes can go down, other nodes pick up the writes for them. It's sort of like when you go on vacation, your neighbor picks up your mail for you, right? So your mailbox doesn't fill up, and then when you get back, he gives the mail back to you. This is exactly what happens in Riak. So if the node comes back, this guy knows that he picked up the mail for this one, and he hands it off. And then as requests come in, the normal operations resume, and it goes back to the original replicas. So this is a common theme. Data is always replicated many times. Nodes can fail, and we still maintain that 3 replica count. So you can lose 2 nodes and still have a copy of your data left. Very quickly, this is how a request sort of plays out in Riak, and this exposes some cool things about the Dynamo concept, how we've implemented it in Riak, and some kind of cool things about the Erlang VM as well. So Riak has clients. You can talk to Riak over HTTP. You can talk to Riak over a protocol buffers interface. We ship clients in .NET, Ruby, Java, Scala, Haskell, Go, and a bunch of, pretty much any modern language, you can find a client. Or if you want to use the HTTP interface, any language that can speak HTTP can be a client for Riak. So here we're in the client's process space. The client says, in this example, it looks like we're storing blocks of some file or whatever. The client issues the request to Riak. The cool thing about Erlang is that you can spawn many, many processes. They call them processes in Erlang. They behave like threads, but they're not as heavyweight as an operating system thread. So on my laptop there, I could probably spawn 1 million Erlang processes in one VM without the machine breaking a sweat. So what we can do, because of that architecture, is actually represent individual concurrent events or processes as individual threads without the need for thread pools or multiplexing different logical events across, a smaller pool of threads. It leads to a very clean programming model. So the client's requesting this key. We spawn a process to handle the request. And we do this hash lookup where it finds out where on the ring the data lives, and that results in the 10, 11, and 12. Just those are the replicas. All right. So then you have the cluster here, and this is sort of zoomed in on one part of that ring. And we have 10, 11, and 12. These are the ones responsible for it. So this little request handling process broadcasts out to all those 3 replicas, hey, give me blocks / big UUID. This is a feature of Dynamo and Riak that I won't get too far into, but you can specify on a per request basis how many of these replicas you want to respond before you consider the request successful. So by tweaking that, you can tolerate more machines going down. If you were to say only ask for 1, it would respond with the first replica that responded. If you say 2, which is the default, it'll wait for 2 and do some reconciliation on the values in case they're divergent to make sure you get a more consistent answer and not a stale one. The lower that value is, the higher the chance that you're going to get a stale response, basically, because we don't insist on everyone agreeing at right time. So 10 responds with version 1, 12 responds with version 2. I won't make Gary move the camera. When I was talking about vector clocks before, consider these, I'll use the Git branching analogy. What these vector clocks can tell this process is that V1 has already been merged into V2. It's like if you were doing a Git merge and you merge the same branch twice, the second one would be a no-op. And that's what the vector clock data structure lets us do. So here we know that V2 is the up-to-date version. The other node had a stale one because maybe it was down when it was last written and it's just come up and given us a stale answer back. So we know V2 is the correct one. The client's told us that it only wants to wait for 2 responses out of the 3 that it could wait for. If it asked for 3, then it couldn't tolerate any nodes being down because we replicate 3 times and it's asking for 3. So now we reply with V2 to the client and it goes on its merry way. It's doing something with this result, or it's processing another request or whatever. But recall that we have this thing called read repair. So remember, this 10 gave us version 1. It was out of date for whatever reason. 12 gave us version 2. This process, even though it's returned to the client, is still sticking around because it has work to do. Riak and Dynamo are eventually consistent databases, not immediately consistent or strictly consistent. That's a scary word. But eventual doesn't mean when we get around to it or we may never get around to it. It means that as soon as it's possible to get around to it, we do it, except we just don't stop the world if we can't do it at a certain time. We always favor giving you the latest value or accepting the right, even if we know not everybody's going to agree on it. So this is a very fundamental, if you heard of the CAP theorem, this is the essence of the CAP theorem here, is that you really have to choose between consistency, being up to date all the time, and availability, being able to accept requests all the time. So we've already returned to the client, but we have work to do. Since we're eventually consistent, we take every chance that we get to bring our database towards consistency. We've replied with V2, and say the other guy, and we always wait for that third response. So here, even though 2 replicas were out of date, we could use the vector clocks to determine that this was the correct answer. And then, since we know that V1 was already merged into our new object, we opportunistically and asynchronously, the client's not waiting for any of this to happen, repair the stale replicas. So now we're consistent as a side effect of doing a read of the data. Just to go into the architecture a little bit, I know I'm going really fast with this stuff. Our website is basho.com. You can read all about this stuff there. Yes?
What if node 11 had returned version 3 instead? You would have served the client version 2, but you're still having version 3.
If the node, yes. Yep, and that's eventual consistency for you.
But then it will update the 2 others to version 3, even though you have given the client version 2.
We've given the client version 2, but the next client is going to read version 3. So let me give an analogy to that. Say you update your avatar on some sort of social network site, right? And then it takes you back to your profile, and you still see the old avatar. That's a normal, that's within the realm of acceptable user experiences. Or you add something to your Amazon shopping cart, and it takes you back, and you look at it again, and it's not there, and you refresh the page. You've seen this kind of thing happen on the web. Or you change a DNS entry, and it takes a couple minutes to propagate. These are all examples of eventual consistency in the real world that we've come to deal with. It's not right for every scenario, but in situations where availability is important, being able to tolerate failure is important, there's ways to make it work. So Riak's written in Erlang. There's 2 client APIs, HTTP and protocol buffers. The Erlang VM is really cool because it allows us to model concurrent activities as actually concurrent processes. If you're writing in Java, you're probably not going to write a scalable web server by, when the request comes in, spawning a new thread for every request. You're going to probably have a thread pool and put requests in some sort of queue, and then the queue handles it, and then you have another queue to get the response back, etc. We can actually just launch a thread for each one and not care too much about it. And there's a different kind of state machine modeled as a process for every different request type. So it's a key value store. The API is pretty simple. There's get, put, and delete, just like you'd have in a hash table in your favorite language. But we also have extras like MapReduce and some other ones that I'll get to later on. The real cool thing, though, is that this is a clustered system. We have Riak clusters. I mean, you can make one as small as 2 nodes. We have customers with Riak clusters that are 150, 200 nodes large. And all the complexity of handling that clustered stuff, and there's a lot of it, all that logic around taking responsibility for other nodes' data when they go down, the whole notion of just membership, how do the nodes know about each other, how do the nodes know how to route requests, etc., is handled in this library called Riak Core, which is the whole Dynamo model, this loosely coupled, eventually consistent, distributed system. But this layer here has no idea that it's participating in a database. It just implements the sort of data structures and algorithms and stuff that that the Dynamo paper talks about, but doesn't really insist on a use case around it. So the code up here on this side doesn't really have to be written in a complicated distributed systems manner. It just says, hey, Riak Core, you know about the cluster and all these nodes. Here's a request. Distribute it in the right way to the right nodes in the system. Riak Core handles that. And then on the bottom, it's an interesting way to use a library because you sort of have to plug into it on the top and bottom. There's a process running for every little piece of the pie in that ring. And those carry out the actions locally on the cluster. So from the top, you say, here, cluster, do something. The cluster said that this, where all the complexity is hidden, says, okay, this has to go to nodes A, B, and C. Here, nodes A, B, and C, here's some work. And then nodes A, B, and C just carry out that work locally. So neither part, each part is sort of ignorant of the fact that there's this complicated distributed systems going on the way we factored it. And there's a JavaScript runtime in there because not everybody likes Erlang, and you can write your MapReduce jobs and all the custom stuff in JavaScript as well. So Riak Core, there's actually several companies, most of them sort of adventurous Erlang shops, that have built custom non-database, high-performance, reliable apps just using the Riak Core part of our architecture. So this talk is really, and I've got 10 minutes, I'm going to sort of blast through this stuff, but that sounds great, but I saw people get visibly uncomfortable when I talked about some of the concepts here, and you weren't wrong to do that, because some of them are extremely uncomfortable. They're necessary compromises if you want that extremely high availability, but sometimes it's worth giving up a little bit of that just for some sanity in how you develop against this thing. Eventual consistency can really suck. What can happen with eventual consistency? That example where we had version 1, 2, and 3, or you suggested version 3, we had versions 1 and 2, was the easy one where we could pick a clear winner. We didn't cover the case where, just going back to the Git metaphor, there was a merge conflict. If that were to happen, you would ask for, key K, and you'd get 2 values back. Like what? If you want to do select one row from a database, you normally get 1 row, right? What that indicates is that, say, half your nodes were split from each other, and you had somebody update, say it was a grocery list. The nodes were fine initially, and you added milk to the grocery list. Okay, cool, everybody agrees. Then a switch dies, and half your nodes are on this side, half your nodes are on this side, but you have clients talking to both sides. And then someone on this side says, add eggs. So now this side has milk and eggs. And someone on this side says, add cereal. So this side has milk and cereal, right? If we insisted on consistency, both of these sides, when you went to add either the eggs or the cereal, would say, nope, I can't talk to the other guy who has the rest of the list, and this is going to lead to an inconsistent situation. But instead, we say, no, we always want to be able to add to this grocery list, both sides accept the right. So then the partition heals, and you go to read the contents of your grocery list. And what you get is 2 values. One of them says milk and eggs, one of them says milk and cereal. This is actually a really easy conflict resolution scenario because you can just union those 2 sets together and get milk, eggs, and cereal. But that's a simple case. It very quickly gets difficult to model more complex data structures than that using this. And more importantly, it takes all that consistency responsibility and gives it to the client. You have to resolve conflicts on behalf of the database. And the key value model is limited in what you can model with it, right? If it doesn't look like a hash table, then you have to jump through some more hoops to model it on a database who exposes the API of the hash table. I won't go through some of the other ones just out of time, but talking a little more about just the limits of the data model. The good part is you don't have to do that. Along with all that nice vector clock information, we also record a regular old timestamp, and the default behavior is just to return the one that has the newest wall clock timestamp. So in that case, if the person adding cereal did it last according to physical time, the result would be eggs and cereal, but the milk or whatever was written on the other side would have gotten lost, right? And if you go through this in your head, there's no way about it. We could have either denied the write with that network partition going on, or lost some data in the case of making it a little easier, or dealt with the conflicting versions. It's even more of a pain if you're a shop that uses many languages, because then you have to write this logic many times. And there's several solutions that have been proposed to this. Bump, which is an iPhone contact sharing app, they wrote a proxy that implements all this logic, and then all their clients talk to that proxy. And you don't have to rewrite that conflict resolution logic all over. One great use for this kind of system, though, is for immutable data. In other words, data that only gets written once and never gets changed again. Pat Helland, big distributed systems sort of pioneer, says accountants don't use erasers. When people want to shoot down the notion of eventually consistent databases, they always say, well, you couldn't implement a banking system with this. And if you've worked with financial systems, you know that's wrong, because when you debit money from an account, it's not a destructive, it's not like there's a row in a database with balance and we forever just change it. No, you have another event or another object that gets created that's a debit. And then everything gets reconciled at some point in the future. Accountants don't use erasers, is Pat Helland's quote, to talk about this. If your ATM machine can't talk to its home base, what it actually does a lot of times is says, all right, I'll give him $200, or I'll feel safe giving you some amount of money and debit it later. If if the financial world didn't use eventual consistency, then it would be impossible to bounce a check. But if the data that you're writing never changes, then you don't have to worry about those conflicts. You're never going to get two values back because nobody's ever changing the data. And you don't need to wait around like we did in that example for all the versions to come back, because there's only ever going to be one version. So one technique for dealing with, for using these eventually consistent stores is just don't change data, simply create a new copy and have a pointer to it, right? The problem then becomes, how do you get rid of the old pointers that point to data that's now stale? But that's, at least that's the database's problem now, not yours. You have to make a distributed garbage collector, which is very hard, but at least we've taken that problem out of the user's hands. So in the several years since these kind of databases became popular, people have recognized these pains, and they've come up, the research community has come up with some solutions. One of them is CRDTs, conflict-free or commutative, depending on what paper you're reading, replicated data types. All that really means is it's doing on the server what you would normally have to do on the client to resolve these things. And how this usually looks is basically, instead of treating a value as just a materialized value, you treat it as an operation log. And you run, if you're familiar with CQRS or event sourcing, this is going to sound familiar. You basically, to arrive at the value, you start with some sort of cached snapshot of it, and then you apply the operations in the log and arrive at what the newest value is. And to change the value, you don't just destructively change the value, you add an entry to this operation log, and then with some metadata about who you are and when you changed it, and then at points where the system knows everything's in sync, you can sort of prune that log and create a new snapshot and continue on. So this is coming to Riak, and that'll give us things like counters and sets, where instead of reading a value, changing it, writing it back, and all this conflict stuff going on, you can just say, hey, increment the set, or increment the counter at this key, or add this item to this set, this key, etc. I'm going to skip by this, skip by that. What we've come to know is that eventual consistency is great for the stuff that can handle it. Your avatar in a social networking site, right? It's fine if it doesn't update right away when you change it. The like button on Facebook, right? It doesn't have to be precise. Lots of things in the web world are fine with eventual consistency. But usually for any one comprehensive use case, there is maybe 50 to 80% of it that's fine with eventual consistency, and another, 20% or so that actually needs, either requires strong consistency or would be a real pain to write in that eventually consistent model. So coming up in a soonish version of Riak, there is going to be strong consistency. So that's what you'd normally expect from a database, where you write something to the database and that value is either accepted and it's true forever and ever, or it's denied and the value changes the same. None of this multiple version stuff. It's just going to be important when we add this, since it's so much easier, people are going to probably want to use it all the time, and they're going to lose some of the availability benefits of the other way of doing things. If this is the kind of stuff that you're into, we had a conference in San Francisco a few months ago called Recon. Recon2012.com has lots of interesting talks on all these kind of subjects. Sort of an interesting aside here. How eventual is eventual consistency, right? Like, how often does this really happen? How often am I going to get those two values back and have to do something with it? Turns out you can predict it. Some of our friends at University of Berkeley made this model and proved it, that if you can measure the different latencies in different parts of your system, you can model how likely you are to read the latest value. And it turns out, if say this is just a simple example, but if you have 0.1 milliseconds latency at there's certain parts of your system that you have to instrument, that if you wait 25 milliseconds, you have, or if you wait 100 milliseconds here, you have a 99.96% chance of being strictly consistent. So the thing about eventual consistency is that it just doesn't enforce it. It doesn't mean that you're not consistent all the time. If you're reading the database only every 200 milliseconds, chances are you're never going to see any of the eventual consistency. It only happens in failure conditions or under very heavy concurrency when you're, constantly writing or reading. One other sort of operational problem, TCP incast, sort of best explained by my coworker's grandfather, is that you can't pour 2 buckets of manure into one. These are lessons we learned from running this kind of database. And this happens in any system, really, where there's replicas happening, where you have a coordinator, and then that coordinator is sending requests to many other nodes. So what happens is, and you saw that sort of broadcast in the earlier slide, the coordinator sends the request, all of the replicas respond at roughly the same time with a largish value. And when that hits the switch has, if it doesn't have space to buffer it, and buffer space, buffer memory on switch ports is very, very expensive, it has to drop packets. And all the TCP flow control mechanisms kick in. And you can see like a 10 gigabit line only getting about 25% utilization. And it's very, very, very hard to even notice what's happening, because you have to really grind down the window of that of events that you're looking at. This puzzled us for a long time. I didn't even know what TCP incast was, but we discovered it. If you ever see unexplainable like bandwidth non-utilization in systems like this, Google TCP incast, and you'll get some good information. I'm not going to talk about vector clocks. I'm going to talk about that. So yeah, just a little bit more about Riak. We added a bunch of things. Dynamo in the paper was just a key value store. We added the ability to do MapReduce in either JavaScript or Erlang, full text search in a manner that looks kind of like you're using Solr or Lucene. You can put secondary indexes on data, because having to look things up by just the primary key all the time isn't easy. You can add what we call pre or post commit hooks, what traditional databases would call triggers. So you can run custom code after certain events happen. This is the thing that we sell, which is the ability to have a data center in Aarhus, a data center in London, a data center in Japan, and one in San Francisco, and have them all talking together for applications that really need a global low latency experience. There's a distributed computation framework for sort of real-time analytics called Riak Pipe, and Riak CS, which is our Amazon S3 clone. Again, the slides, it's bit.ly/NoSQL Aarhus, hosted on one of our test clusters for Amazon S3. This is sort of the future of Riak. Nobody really wants to code against this eventually consistent database that's all complicated with all these options. But it turns out it makes a great foundational layer for building much simpler database-like things on top of it, and one of these is Riak CS. So S3 is a much more constrained, simple, understandable API. You know, put large files into it, you get large files out of it, they're organized in buckets. Everybody knows and loves S3. And this really was the first time we tried to, I mean, we've all written, at Basho, we've all written apps against Riak and experienced the pain of having to write against a database like this. But this really made us realize that sort of the way to go in the future is much simpler databases written on top of the big featureful, complicated one. And we're almost running out of time. Riak Core, if you're interested in distributed systems research, this has all really the hard stuff in it. It's its own separate GitHub repo with its own separate project. All the actual applications that you deal with when you're talking to Riak are basically plugins to this framework called Riak Core. OpenX is a very large ad serving company. They have 300 or 400 nodes of a custom Riak Core app running for doing impression counting. StackMob is a mobile backend as a service company. A lot of their stuff is written in Riak Core. Problem with it is that it needs to be a lot better documented. You have to sort of be an Erlang cowboy to play with it now. Multi-data center replication, we're basically out of time, but the multi-data center replication that we sell is much more optimized for WAN links that are going to drop a lot more packets than your local data center. So Riak actually comes with two different sets of replication algorithms. One optimized for in-data center, low latency, high throughput. One optimized for long haul, unpredictable, lossy links. And then finally, Erlang. It's a great language for this stuff. I started my career at Akamai writing distributed systems and did more of them at Apple, and I didn't discover Erlang until I got to Basho. And I know for a fact if we had Erlang at Akamai back in the day, we could have saved a couple $1 million in development by poorly re-implementing stuff that Erlang provides. First-class support for distribution transparently across multiple nodes, lightweight processes, very easy to just saturate a multi-core box by modeling your problem as a bunch of independent processes. And if you're into Erlang, github.com/Basho. It's not just Erlang, we have a lot of cool open source stuff there. And that's where we are. So quickly, part of the future, Riak has no security model built in. It's up to administrators to firewall it off. We need to add a security model to it. Support larger clusters. Everybody wants to have hosted services now. Riak has no way of implementing fairness. Somebody can run a MapReduce job that uses up all the cluster's resources, and user 2 is starved. These are standard sort of distributed systems problems. And the real answer is use Riak as the sort of hidden foundation for much simpler cloud services. And that's a quick version of this presentation. I wish I had time to go through it all, but to the extent that you have any questions on that, I'd be glad to answer them. Again, these are our links. I'm at RB0 on Twitter. We're hiring all over the world. If this is your kind of thing, you don't have to know Erlang. And you can read much more about Riak at docs.basho.com. Thank you. Any questions? Yeah.
So, you're familiar with any good resources that take a sort of reasonably complex real-life situation that I might know well in a relational database idea or train of thought, and then actually model out the entire data model for something like, I don't know, blog engine or something like that
In a story like this?
Riak-ish way, or what?
Yeah, we have some examples on our blog. I think there's an example of a Twitter clone on our blog somewhere. There's an example of image store URL shortener thing. Usually, you know, maybe I'll try this way. Have you ever have a table that you've denormalized so much that it's just the primary key and then maybe some compressed XML in a blob column, or seen or heard of these types of things? You know, maybe it started out very...
Heard of them as an evil rumor, yeah.
Yeah.
No.
Those are the type of things that you know, that I've seen on a couple sites. If you're only doing primary key lookup on something and that's becoming a bottleneck, then that's a good target for Riak. The truth of the matter is if you're getting by with your relational database, use it, because this stuff is much more complicated. And if you're not getting by in your relational database, like, buy some SSDs and buy yourself some time. Eventually, you know, our long-term roadmap, I was asked today where Riak would be in 5 years, and I think in 5 years, you'll be able to talk to Riak with a SQL interface, because we'll gradually build back to where we were, you know, when all these databases sort of broke from the tradition. But until then, you know, if you can get more gas out of a relational database, definitely do it. But you'll know when one of these problems hits you. When they really do run out of gas, then it's, you know, then the first tables that people tend to migrate are those just lookup tables of key value pairs. But there's, for more sort of relational, how they relate to Riak issues, there's on our website, there's a case study of a company that went from MySQL, relatively complex application. It wasn't a blog, it was like a cloud monitoring app, so it wasn't some data model that we're all sort of familiar with, but they talk about how they moved from that to Riak. So from relational to Riak white paper we have on our Basho.com website. Anyone else?
I know that some big sites use MongoDB. What are you solving that they're not able to?
Sure. So what MongoDB does, well, there's a couple things. MongoDB, you still have this problem where you have a master and a slave. It's very hard to scale writes out in MongoDB because all the writes have to be funneled through a master, right? So if you have a workload that you can't funnel all that traffic through one master, then you have to do shards, and that becomes sort of complexity that bleeds out into your app. Not that Riak doesn't bleed complexity out into your application, but then you shard and you choose a shard key, say the first letter of a person's last name is a simplified example, but you have a machine for the A's and the B's and the C's and the D's. Well, unless you pick a shard key that has a nice uniform distribution, then you have like the Justin Bieber machine, right, or some popular pop star, right, getting way more traffic over time, and you have a hard time minimizing hotspots. I'm going to be diplomatic about the other issues with Mongo and data loss, but if you like search for MongoDB data loss versus Riak data loss, draw your own conclusions there. MongoDB is great because you can fire it up and get really quickly up to speed on an app with your laptop without all sorts of object relational mappers and crap middleware in the way, right? But when it starts to hit very, very high traffic is when we get a lot of customers, I can only really speak from experience, coming from Mongo to Riak. Mongo's definitely more friendly for developers. Riak's more friendly for operations. It's another way you can say.
Is there anything like a caching layer or anything like that thought in Riak now? I don't think there is, or is anything like that on the roadmap? Basically a replacement for memcached or something like that?
Yeah, I actually wrote, and I don't know what I did with it, it's on GitHub somewhere, a layer on top of Riak that actually implemented the memcache protocol. There's no explicit cache in Riak, although it can be used pretty effectively as a big distributed cache because we opted for a simpler design where we basically just leverage the operating system buffer cache, right? So for the right kind of workloads, you're going to be getting those reads served out of memory anyway because we have a very simple on-disk format that's very friendly for, say, like the Linux page cache to just read in. And we give the page cache hints, like if you delete a piece of data, we say, hey, evict it. So we sort of use the file system's VM cache as our cache. And the API is very similar to that of like a memcached. The things that we didn't, when I wrote the memcached layer, the things that we don't have, somewhat obviously, are things like compare and swap, because that's something that needs strong consistency that we don't have. But when we add the strong consistency stuff in, it will be possible to probably implement a faithful memcache, feature-complete memcache API. The other thing is that the HTTP API is very cache-friendly. We generate and honor all the right e-tag and conditional headers, so you can just put a squid or a varnish or an nginx or something in front of it, and it'll just naturally sort of play nicely with it. Anything else? Cool. Well, thank you guys for coming out. Again, check out the NoSQL Search Roadshow and give Tony Falco, my old boss, a hard time. Did you have a question? Sorry. Thanks. All right, thanks a lot.
Yeah.